Our next speaker is Kevin Milans, and he is going to talk about binary subtree with a few fun labels. Thank you. He's from US Ecology.
So thanks very much. I'd like to thank the organizers, Rigo and Leandro, for inviting me out and giving me this opportunity to share some of my work with you. So I'm a discrete mathematician, so we'll be talking about a combinatorial problem, although it did arise in the context of a problem in another area, in computability theory. And the context in which it arose, I think, is also very interesting. Unfortunately, we don't really have so much time to get into it, but if you like computability theory and you're interested, please don't be shy about coming up and asking me during one of our breaks. Okay, so let me tell you about the combinatorial problem. It's a problem where we're dealing with ternary trees. The edges of the trees are labeled. Each edge is labeled with a 0 or 1. And all of the leaves are at the same distance from the root. Okay? So here's an example of one such tree. The root is up here at the top. And all the leaves here are at depth 3. Okay? And we call the family of all such labeled 0, 1 edge-labeled ternary trees, that's denoted by script T sub n. Okay, so this is one example. This is one member of script T sub 3. The 3 corresponds, of course, to the depth there. Okay, so those are the objects that we're studying. And if you look at a path from the root of this tree to any leaf, well, the edges along that path are labeled. They come with labels, either 0 or 1 for each edge. And if you read out the labels along the edges in the path, you get what we call a path label. So for example, here's your root. If you look at the path from the root to this leaf over here, the path label is 1, 0, 0. It's just a bit string whose length is the same as the depth of the tree. In this case, that's 3. 1, 0, 0, path label for that path highlighted in red. Okay. So we're going to be looking for binary subtrees which don't have too many of these path labels. So a little bit of notation, and there's one more coming. Script B for binary, script B of T is the set of all complete binary trees, okay, of full depth. So let me show you an example of one member of B of T. Here's an example of one such binary subtree. So you notice that, okay, at the root we have 2 children, right? In fact, every non-leaf has 2 children. Okay, so that's how binary subtree looks. And then we're looking to minimize the number of path labels that occur in our carefully selected binary subtree. So we'll introduce some notation for that. L of S for a binary subtree S. L of S is just going to be the set of all path labels that occur in paths in S. Okay, so for example, for this binary subtree here, this highlighted tree S, what's L of S? Well, let's see what path labels occur. So over here, we have 0, 0, 0. Okay. Over here, we have 1, 1, 1. So 0, 0, 0 is there from paths along, going along here over to the left. 1, 1, 1 from coming along down here. And we also have 1, 0, 1 if we head off to the right. Okay. So by the way, just some notational conventions. I use T, right? Regular Roman T, that'll stand for one of these ternary trees. I use S, that'll stand for a binary subtree. So that's the notational convention. Okay, and here we found a binary subtree which has 3 path labels. Of course, the number of paths, it's always going to be 2 to the depth, right? But the number of path labels might be less. Okay. All right, any questions about any of the notation up here or anything like this? Okay, so we're looking for a binary subtree which minimizes the number of path labels, so we'll have a notation to capture this goal. So f of t, that's going to be the minimum of the size of the path labels occurring in a binary subtree of t, right? So it's the minimum over all possible binary subtrees that you could choose of the number of path labels that occur in the subtree. Okay, so for example, for this tree here, this particular binary subtree, we found one that only uses 3 path labels. So that's showing that for this tree, f of t is at most 3. Okay, but we might be able to do better. In fact, in this case, we can do better if we selected a different subtree. Okay, so if instead we selected this binary subtree, I'm calling S prime, if we selected it, then we would only have 2 path labels. If you look at the path labels in this binary subtree, we've got zeros, all zeros along here, if we branch off to the left. And over here, if we go off to the right, we only have 1, 0, 1. Okay. And in fact, for this tree, this is the best that you can do. You won't be able to find any subtree which only has a single path label. It doesn't exist in this tree. Okay. So, and the final definition is that we're looking for, in some sense, the worst case over all possible ternary trees. So for each n, we define f of n, it's the maximum. It's the maximum of f of t, right? So it's the, in the worst, if you look at it from the point of view of someone who wants to minimize the number of path labels in the binary subtree, if someone gives you the worst possible ternary tree, and then it's your job to find the best possible binary subtree, and whatever that value is, that's f of n for tree of depth n. Okay. So one observation, right? No matter what ternary tree I give you, if you choose any binary subtree at all, it's going to have at most 2 to the n path labels, right? Because there are only 2 to the n bit strings of length n, right? So even in the worst possible situation, no matter what you do, you can't get more path labels than 2 to the n. Okay. And the question that we wonder about, which is particularly important in our application in computability theory, is whether or not this ratio, f of n over 2 to the n, how does this behave as n grows? As our trees have increasing depth, as the depth increases, what can you say about the number of labels you'll be able to find in binary subtrees? In particular, we hope here, what this limit is saying, we hope it's the case that as long as n is very, very large, as long as n is growing, no matter what kind of ternary tree you're given, no matter how the edges are labeled, you'll always be able to find some binary subtree, at least one, which has a vanishingly small fraction of the path labels. Okay, vanishingly small fraction of the space of all 2 to the n possible bit streams occurring as path labels in that carefully selected binary subtree. Okay, so that's the setup. That's the setup. And I want to tell you a bit about how we prove the upper bound. So what's our goal, right? Our goal is to show that no matter which ternary tree we're given, no matter how those edges in the ternary tree are labeled, we'll be able to find a binary subtree which has few path labels. That's our goal in proving an upper bound on f of n. And we'll need 2 lemmas. We'll need 2 lemmas which have the core concepts, and then we'll build on them a little bit. Okay, first lemma, I like this a lot. Call this the monochromatic subtree lemma. So it's not originally due to us. Oh, goodness! I just recall I forgot to mention my my co-authors. So yes, this is joint work with Rod Downey, Carl Jacques, and Noam Greenberg, who are computability theorists. So this is not originally due to us. It appears in, well, at least in two other places prior to our work, but it's kind of nice. I think it's nice. If you ever teach a class in induction, this is a very, very nice exercise that you could give. Okay, so here's what the lemma says. It says if you have a ternary tree where now the leaves come in one of two colors. So every leaf is either red or blue. And the statement is that you're going to be able to find sub-binary subtree such that every leaf in the binary subtree is either red or every leaf in the binary subtree is blue. Right? So all the leaves are monochromatic in this binary subtree. And probably while I'm speaking, maybe some of you already see the proof, right? So no words in this proof, just a picture. So you have some ternary tree and all the leaves are colored either red or blue. So inductively, find monochromatic binary subtrees of the subtrees that are children of the root. Okay, so by induction we can find a binary subtree, monochromatic binary subtree over here in this tree. In this case it's blue. And similarly by induction over here, a monochromatic binary subtree in the middle tree and over here on the right. Well, we only have two colors, right? Those binary subtrees either come in blue or they come in red. There's no other possibility. And we have three children at the root. Well, okay, two of them have to be the same color, and there you go. You choose those two branches to be part of your binary subtree. Okay, so that's kind of nice. Okay, so, all right, that's one lemma that we'll put into our toolbox. The next lemma we need has to do with what we call orthogonal partitions. So let me tell you about those. So we're working with a ground set, epsilon, just a finite set, and we're going to be considering partitions of this ground set into two parts. So, and if you have a pair of partitions, x and the complement of x, the complement always with respect to the ground set, right? X and the complement of x and y and complement of y, we say it's alpha orthogonal if you look at all four of the cross intersections. X intersect with y, x intersect with the complement of y, so on and so forth. If they all have size at least, well, alpha times size of epsilon over 4. Now, y over 4? Well, it's just normalized so that the best possible, the most orthogonal that any two partitions can be, well, if you think about it, right, these four sets are going to partition the ground set, right, into four sets. So, of course, the best possible situation would be if they each had a fourth of the size of the ground set. Okay. All right. So if we would like to draw a little picture, and it looks like this. So this rectangle represents the ground set, and we look at the partition. Maybe this one's a better marker. Yes. Look at the partition of the ground set into a set X and its complement, and then we look at another partition. Y, then what we want is that all four of these possible boxes have size at least 1/4 of the total number of elements in the ground set. Okay. All right. Okay, so we say that a family of partitions is alpha orthogonal if it's the case that every pair of partitions in the family is alpha orthogonal. So just to give a little example, suppose our ground set happens to be the n-dimensional vector space over the field of two elements. Okay? And for each for each element in the ground set, we let x sub z be the set of elements, the set of vectors, which are orthogonal to z. Okay, so that gives us a subset of the ground set. And if we collect all of these partitions for each such z, throwing away the zero vector, right? Okay, so we're not going to, I mean, the zero vector is not interesting. If z is the zero vector, x sub 0, well, everything is orthogonal to the zero vector. Okay, so if you look at this family here, in fact, it's not so hard to show that this is going to be a 1 orthogonal family. And what's the size? How many partitions do I have? Well, I have 1 for each non-zero vector. So that would be the size of the ground set minus 1. And it's a nice little exercise to show that you can't find a larger 1 orthogonal family. Okay. All right. But, so the idea is that we'll want large alpha orthogonal families. This isn't going to be large enough for us. If we're willing to relax this requirement alpha, if we're willing to go down from alpha equals 1 to a smaller value, then we can find a lot more. And that's what this lemma is saying, that as long as you're willing to tolerate a little bit of error, not divide the ground set into 4 exactly even parts, but 4 parts which are somehow close to being even, then you can find exponentially many partitions to form your alpha orthogonal family. Okay? And the proof is very natural, straightforward. All you do is you just choose your partitions at random. Right? If you think about it, if you choose partitions at random, then it's quite likely that the picture will look like this, right? If you have a large enough ground set and you choose x at random and y at random, it's quite likely that you'll have a reasonable size in each one of those 4 boxes. Okay, so that's how the proof goes. So as long as we're willing to accept some imperfection, have alpha a little less than 1, we can find very, very much larger, right? Much larger, exponentially large in the ground set, whereas if alpha equals 1, we can only get, well, less than the size of the ground set. Okay, so now let's take these two. I want to show you how these two ideas can combine and give us the an upper bound. Okay, so the idea is that we're going to consider k ternary trees, and we're going to find binary subtrees in all of them, such that the union of all of the path labels used in any one of those subtrees that we select, right, the union has small size. That's going to be the idea. And we're going to be able to do this as long as we can find a large enough alpha orthogonal family of partitions. Okay, what does large enough mean? Large enough means it's with respect to how many ternary trees we're given. So you're given k ternary trees. As long as you have a large enough family of alpha orthogonal partitions, we'll be able to find binary subtrees in all of them, okay, such that the union of the path labels is bounded away from the size of the whole space of 2 to the n vectors that could possibly occur as path labels. Okay, so let's take a look. How does this work? All right, so here we go. In this example, in this picture, k is equal to 4. So there are the 4 ternary trees that we're given. We need to find the binary subtrees. What are we going to do? Well, let's look at our alpha orthogonal family F. Let's pull out the first partition from F and play with it. Okay? So x1 and the complement of x1, member of our alpha orthogonal family. What are we going to do? Well, next we're going to, for each one of these trees, and for each leaf in this tree, we're going to give it a color, red or blue. What color is it going to be? Well, it'll be red if the path label from the root to the leaf happens to fall in this set x1, and it will be blue otherwise if it falls in the complement. Okay? So that's how we're going to color all of these leaves. Now we've colored the leaves with two colors. What do we know about ternary trees whose leaves are colored red or blue? Well, they have monochromatic binary subtrees, right? So under this coloring of leaves, we'll be able to find either a red binary subtree or blue binary subtree, and that's true of each one of those trees. Okay? So that kind of partitions the trees that we're given into two classes, right? Those that have red binary subtrees and those that have blue binary subtrees. Now remember, we have a lot of partitions. So let's just do this again and again for each one of, we have a lot of partitions in our alpha orthogonal family. So let's do this again and again, once for each one of the partitions in our alpha orthogonal family. Okay, so maybe if we do the same procedure with the second partition, we get some blue subtrees here in the first two trees, and maybe in the second two trees we get red binary subtrees. We do it again, we might get a different pattern of red binary subtrees and blue binary subtrees. But if we do this enough, by the pigeonhole principle, we'll eventually find a pair of partitions in our alpha orthogonal family that give the exact same partition of the trees that we're given. Okay, so for example, these two here both have the property that, well, in the first tree they're both giving red binary subtrees, and in the last three they're both giving blue binary subtrees. Okay, so let's see what we've got. Well, what did it mean for this to have a red binary subtree? Well, that meant that all of the path labels in this binary subtree are inside of the first part in this partition. And what did it mean for all of these guys to have blue binary subtrees? That meant that all of the path labels in those binary subtrees are in the second part, complement of y. Okay? But now if you think about it, then any path label, if we select the red binary subtree here for T1, and we select the blue binary subtrees for the remaining trees, if you think about any path label in any one of those binary subtrees, it either has to belong to X, right, if it came from a red tree, or the complement of Y if it came from a blue tree. Well, this is great because, okay, no path label was used from the complement of X intersect Y. Right? We didn't use any one of those path labels. But we took these partitions from our alpha orthogonal family, which means that this is large. So we avoided a large set of path labels that don't occur along any of the paths in the selected binary subtrees. Okay, so that's the main idea. If we put this together with a lemma which gives us large alpha orthogonal families, then what we'll be able to do, we'll be able to prove this lemma here, which says that as long as the depth of these trees is large enough, as long as the depth of those trees is large enough, we'll be able to find our binary subtrees that use few path labels. Okay, at most, like 3/4 plus a little fraction plus an epsilon, that fraction of the total space of all of the possible all the possible bit strings. Okay. So just a little note, the assumption on the depth is best possible up to a constant. All right. So with this in mind, let me show you how we actually construct the binary subtree. So if we're given the ternary tree, how do we actually find the binary subtree? So there we go. There's the picture of our tree. We look at the subtree consisting of all of the levels from the root all the way down to a depth, well, we shave off some fraction, constant fraction times root n. Okay, so we go down a fair bit of way into the tree. We apply induction and find a good binary subtree here, good binary subtree of t prime, and then we're going to extend at each one of the leaves. And essentially there are two possibilities. Either we have a lot of paths here that have the same path label, in which case we're very, very happy to extend anyway, because if you think about it, if you've already gotten a huge number of paths with the same path label, all zeros, for example, then we're already doing very, very well, and we can extend in any way, and we'll still be fine. On the other hand, if we have not very, very many of these trees here, not very many of these leaves with the same path label, then we're in a situation where we don't have too many trees, but we've saved enough space down here that we have enough depth to apply the previous lemma. And we can extend efficiently in all of those subtrees and avoid introducing too many more path labels into our binary subtree. Okay, so I'll just outline, since I'm running a bit short on time, I'll just outline the results for the lower bound. Here's our best lower bound. Our best lower bound is, well, it's at least growing exponentially. The base of the exponent is about 1.54, 1.55, somewhere in that neighborhood. It would be very, very interesting to improve that lower bound. There are a number of generalizations. You could talk about if you, instead of having a ternary tree and searching for an efficient binary subtree, you might have trees of larger arities. You might have, say, a tree with branching factor 4, and you might be trying to find a subtree with branching factor 3. Okay. So there are many questions we don't know the answer to. These are open problems. Okay, I should say you have to use more labels. With 2 labels, the behavior is completely known. Okay, so just to summarize, our lower bounds here, we have exponential lower bound, which is the base is less than 2. The upper bound, we don't have any better base than 2, but we are able to show that it at least tends to 0. You divide by 2 to the n. We're able to shave off some constant times root n in that exponent there. But this limit here, which we do know exists, is somewhere between this 1.55 and 2. It would be very, very interesting to know in particular if the limit is 2, if the limit meets the upper bound. I am beginning to suspect that the answer is no, that we should be able to improve this upper bound, but so far we don't really have techniques to manage that. Okay, so there are many, many open problems. Thanks very much for your attention.
Any question?
In one of the earlier slides, you used a standard notation for the inner product, showing that you had orthogonality 0. And since it's not computational in a sense, I wonder if it's not orthogonal, do you have any numerical way of representing it? Do they vary? One of the, there it is, right there.
If the family is not orthogonal, do we have a way to represent it? Well, I'm not completely sure what you mean by that.
All right, you've got your inner product to 0, right?
Mm-hmm.
Okay, so that's definitely orthogonal. But if you have non-orthogonality in the usual algebraic sense, it's going to be something other than 0.
I see.
And
Okay.
all I'm wondering is if there is anything related to that in what you've done here.
Okay, so that's a very, very interesting question. So let me see if I'm understanding you correctly. So I think you're suggesting, what if we don't require that this is equal to 0 exactly, but what if we were to require that it was, say, small, maybe some bounded constant? Would that also give you an alpha orthogonal family if you looked at those partitions? I don't know. I'm not sure.
I'm not sure I explained it exactly so that you could even give an answer. But you know, if you deal with orthogonal functions, of course, It's clear, for example, from Fourier analysis that you're not going to get 0 all the time. And so I was just curious, when you say they're orthogonal, do you just assign the value 0, or is it computable?
When, so we've constructed an example here, right?
Okay,
It's an
right.
explicit construction. And the definition of it is just, we include all of those that happen to be orthogonal to Z. That goes in the set X sub Z.
Okay.
Yeah. Yeah, so, right, so it's just whichever ones happen to be orthogonal to Z, those make it into that set. Does that answer your question?
Yeah, I think so.
Okay, thank you very much.